Welcome to the online wastewater treatment operator certification training event. I'm Jason Flowers with Geosyntec Consultants, and I'm presenting this on behalf of the Arizona Department of Environmental Quality. The material presented in this training event will be covered under 5 modules. First module is Introduction to Wastewater Treatment, Water Quality, and Laboratory Analysis. Module 2 covers preliminary treatment. Module 3 will cover primary treatment. Module 4, secondary treatment, and Module 5, disinfection. The objectives of the presentation include discuss principles of operation and maintenance, establish operational and maintenance knowledge baseline across ADQ permitted wastewater treatment plant sites, and to increase technical and operational adeptness across ADQ permitted wastewater treatment plant sites. The format, as we mentioned before, is a series of modules that will be covering basics of wastewater treatment. Material in these slides were put together by a team of people at Geosyntec, including Kirk Craig, Vanessa Maldonado, Catherine Mays, and Emily Yates. This work was also done in collaboration with Tina Piku, who's the Operator Certification Program Coordinator, and Rona Malay, who's Project Manager with the Groundwater Protection Section. Moving into our first module, Introduction to Wastewater Treatment, Water Quality, and Laboratory Analysis. As we begin, we're going to provide a general summary of wastewater treatment process. The wastewater, which has been collected throughout the collection system, is conveyed to the wastewater treatment plant through a series of trunk lines and pump stations. Once it reaches the wastewater treatment plant as raw influent, the wastewater first goes through preliminary treatment to remove rags, sticks, grit, and grease. Then some plants will have primary treatment, which will remove heavy suspended solids as well as sellable organic material. Next will be secondary treatment, which will remove soluble biodegradable organic material and nutrients, including nitrogen and phosphorus. Finally, there'll be tertiary treatment, where disinfection is used to remove pathogens, and sometimes you'll have residual suspended solids removal through tertiary filtration as well. This presentation will not cover solids handling, but that will be covered in future training events. Next, we're going to move to water quality and laboratory analysis, which affects the entire plant. Now we're going to move on to wastewater quality analysis. The purpose of wastewater quality analysis is, number one, to measure efficiency and improve process control of your wastewater treatment process. And probably more importantly, is overall compliance with their discharge permit limits, including your ZIPDs or APP permit, depending upon your wastewater treatment plant. Now, where to sample, number one, of course, is to sample the regulated sample locations in your permit, whether that's influent or effluent, or also any other specific permit sample locations, including alternative outfalls or maybe biosolid sampling or whatever else may be in your permit that you're required to sample. In addition to that, sampling key points in your wastewater treatment plant to provide better operational control is also useful, including sampling your primary clarifiers, aeration basins, secondary clarifiers, recycled streams, and solid streams.
So moving on to how you take the samples and analyze for them. First, you have to take the physical sample. That can be a grab sample, in which you just collect a sample at a moment in time and analyze that sample. Or there are composite samples, in which you take samples over a longer period of time and combine them together to get an overall average of how things perform. And we'll be talking about that more later. Once you collect the sample, then you need to analyze the sample. And the analysis can be everything from measuring the weight through using scales, measuring the volume through graduated cylinders or some other means to measure the volume, density, which you calculate by that weight and volume measurements you've collected, concentration, which is something calculated through laboratory equipment, or it can be specific probes that you have that measure things like pH, temperature, and dissolved oxygen directly in the sample. Now, why do you want to collect these samples? Well, first, you want to understand how your treatment plant is performing, make certain it's meeting the targets in terms of how you expect the system to operate. But then lastly, of course, there's compliance with your permit requirements, what you're required to sample to make sure that you're meeting your APP or ZIPD's discharge permit requirements.
As part of laboratory analysis, we're going to need to do some math as part of this. You're going to need to be able to multiply, divide, do some basic algebra, solving for unknowns, and also do unit conversions, which is one of the more frequent things to do. What unit conversions are ways in which we can compare values between different unit formats, whether that's converting pounds to kilograms or cubic feet to gallons if we want to try to measure like how much something is compared to like a permit limit. Sometimes we first measure in another unit like cubic feet, but we need to convert to gallons so we can make sure that we do not exceed our discharge limit in terms of gallons per day, the case may be. Now we're going to cover some measurement units that are used frequently as part of wastewater treatment plant analysis. First, we're going to cover volume. A couple of standard unit conversion rates we use. 1 gallon is equal to 3.785 liters. 1 cubic foot is equal to 7.48 gallons. In terms of mass, 2.2 pounds is equal to 1 kilogram. Moving on to density. With density, 1 gram per cubic centimeter is equal to 1,000 kilograms per cubic meter. And when we think about water, this is one of the more important unit conversion factors, interestingly, is that with water, 1 gallon is equal to 8.34 pounds, or 8.34 pounds per gallon is the density of water. And that unit conversion factor is used frequently in wastewater treatment as well. Now, some basics about SI unit conversion. So when we think about water, and this is specifically for water itself, 1 gram is equal to 1 ml, just based on its density. 1 gram is 1 ml. But some other basic unit conversions for SI or SI units is 1,000 milliliters is equal to 1 liter. That also applies for 1,000 milligrams is equal to 1 gram. And 1,000 grams is equal to 1 kilogram. Same applies for liters as well. 1,000 liters is equal to 1 kiloliter, although I've never heard anyone use kiloliters before. Moving on to concentration. Concentration is the amount of substance in a given volume. One standard unit is 1 gram per liter, but more frequently, when we think about wastewater components like suspended solids, BOD, we're talking about 1 milligram per liter, which is equivalent to 1 part per million parts of water. So 1 part of TSS in a million parts of water is 1 milligram per liter of TSS in the situation. Now, you can go 1,000 times more dilute than that and go 1 microgram per liter, which is 1 part per billion. And when we're talking 1 part per billion, we're talking about typically much more smaller dilute constituents. Think about like PFAS is a common one, which we're talking about concentrations in the 1 part per billion. You can go another 1,000-fold more dilute than that and go to the nanogram per liter concentration, which is a part per trillion as well. So for an example problem for unit conversions, how many pounds does a 3-pack of 2-liter soda bottle weigh when you ignore the weight of the bottle itself? So to do this, first we need to calculate the total number of liters of soda that we have present. And we need to convert those liters of soda to gallons, and then use the unit conversion to calculate the pounds in gallons by using the density of water. So as we talked about before, we need to convert the liters to gallons in this first step of this problem. In this example, we have 2 3-liter bottles of soda. So 3 times 2 is 6 liters of total soda that we have present here. Now, as you see here, we wrote out the units while we're doing this math. And I want to state that's really important because using the units allows you to keep track of which units you're using and what the ultimate solution will be, as you'll kind of see as we walk through this example here. So as we talked about before, 1 gallon of volume is equal to 3.785 liters. So we write this out to solve for gallons we want to solve for in this case here. So if we divide the 6 liters by 3.785 liters per 1 gallon, in this case, the units of liters cancel each other out because they're at the both top and the bottom, which leaves us with gallons at the top. So now we know we're solving for gallons. So in this case, we take 6 divided by 3.785 liters. That tells us we have 1.6 gallons of volume that we have here of soda. Now we need to convert those gallons to pounds. So we're going to also write the units because it helps us to track this. So we start with 1.6 gallons, and we convert this to pounds. We know there's 8.34 pounds of weight in 1 gallon of water here. So if we track the units again, we're going to put the gallon at the bottom. That way the gallons cancel each other out. So now we're multiplying 1.6 gallons, 1.6 times 8.34. Pounds are all that we have left. And so now we're left with 13.3 pounds of soda we've solved for. So this is an easy way to do it, and using the units helps you keep track
of what unit you're using and make sure that you divide or multiply by the right number.
Now, moving on to wastewater quality parameters that are important when we're considering the operation and compliance of your wastewater treatment plant. We're going to cover multiple categories, including nutrients, which can include nitrogen and phosphorus, solids, which can include total solids, total dissolved solids, total suspended solids, and volatile suspended solids. Organics, whereas we measure them in oxygen demand, which can be measured either as biochemical oxygen demand, carbonaceous biochemical oxygen demand, or chemical oxygen demand. Next, physical parameters such as pH and temperature, and finally, pathogens as indicator species. Starting off with solids. Solids can be measured either for operational analysis or also permit compliance. And if you think about solids, you can think about total solids starting off. This is the biggest piece, and this is any solid material that is present in a sample. That can include total suspended solids, which are your undissolved solids. And typically, total suspended solids is what we require to measure for permit compliance. And total dissolved solids, which are any solid material that is dissolved in water. Imagine putting salt into water. That is dissolved solid in that case. Now, as I said, total solids is the combination of total dissolved solids and total suspended solids. Most of the time, we just measure total solids when thinking about solids handling and about solids disposal, like biosolids. We measure that in total solids just for ease of operation, ease of measurement. Now, total dissolved solids really is not going to be important for most wastewater treatment plants, but may become important in the future for direct potable reuse operations. But that's not covered for today. We're going to largely be focusing on total suspended solids and two main fractions of it: inert suspended solids and volatile suspended solids. These are measured for operational control largely. Moving on to how we actually measure total suspended solids. As you can see in the equation above, total suspended solids is equal to the weight of a dry filter plus residue on that filter in milligrams per liter minus the dry filter before anything's added to it in milligrams per liter divided by the sample volume in liters. So that would give you a concentration of total suspended solids in milligrams per liter. Now let's walk through how you actually measure this in the laboratory. First, you start with the dry filter that you'll then collect and take a weight for that sample of that filter. Then from there, you'll put that dry filter into some type of vacuum filtration system, similar to what I've shown here before with the little cylinder at the top. You apply the vacuum and you pour a measured amount of sample through that filter. You'll need to know the exact volume that's measured there. And from there, you'll take that wet filter after it's all filtered through and all the water's been poured through. You'll take that wet filter and put it into an oven at 105 degrees C for 2 hours to allow it to dry. After that, you'll then weigh that total suspended solid, that filter, which includes the residue that's on the filter plus the filter itself. Now that you know the weight of the filter, after the samples run through it, that's your dry filter plus your residue, and you know the weight of the dry filter by itself, and you know the amount of sample that was put through that filter apparatus, you can then apply those numbers to the equation above to determine what your total suspended solids concentration is. To measure the volatile suspended solids and the inert suspended solids, you take that exact same dry filter from the previous slide and put that in a muffle furnace at 550 degrees C for 2 hours, at which point any of the organic material will be ignited off, and all that's left on that filter is the ash, which is the inert suspended solids that's left on there, and the filter itself. And so then you take that sample out and you'll weigh that filter, and that will give you your value of ignited filter plus residue. Then using that number, we can calculate what the inert suspended solids. So look at the equation below for inert suspended solids. You take that ignited filter plus residue weight, as we just measured, subtract from it the dry filter weight on the previous slide, so the filter before the sample was even poured through it, and divide that by the sample volume, and that will tell you what your inert suspended solids is. And once again, this is the material that is non-organic. This is like the ash and metals and any grit that's in your sample. That's what the inert suspended solids will tell you from there. To be able to estimate what the volatile suspended solids is, which the volatile suspended solids is your measurement of the organic content of the sample, you'll take the total suspended solid sample subtract from it the inert suspended solids, and what's remaining is organic fraction, and that tells you your volatile suspended solids. Another key parameter that facilities can measure is the percent volatile. And sometimes this is measured for looking at the influence of the wastewater treatment plant, or frequently in the aeration basins to see the percent volatile in there, which gives you an idea of how much organic material is in your sample. And you measure that by dividing the volatile suspended solids concentration in milligrams per liter by the total suspended solids concentration in milligrams per liter, and multiply that by 100%.
Now let's walk through an example calculation for determining the total suspended solids of a sample that was collected. In this example, you collected a 100 ml sample from a site, and then you run that 100 ml sample through a filter paper under vacuum that weighs 0.5 grams before you run the water through it. The weight of the wet paper is 1.5 grams, and then the wet paper is then placed in an oven at 105 degrees C for 2 hours.
The dry weight of the paper plus the residue is now 0.75 grams. What is the TSS in milligrams per liter of the sample? So at this point, we have the equation. We got a series of measurements we've collected. So now let's walk through this calculation. The first thing we must do is convert the mass from grams to milligrams and convert the sample volume from milliliters to liters. So using the equation we had before, the total suspended solids is equal to the dry filter plus the residue minus the dry filter divided by the sample volume. So in our example, the weight of the dry filter plus residue is 0.75 grams. The weight of the dry filter itself is half a gram. So we subtract those two from each other, and that gives us 0.25 grams. But we want this in terms of milligrams. So we take the 0.25 grams multiplied by the 1,000 milligrams divided by 1 gram. In that situation, the grams will cancel out, and it'll leave us 250 milligrams on top. On the bottom, we have 100 milliliters, but we need to convert that to liters. So we divide that by 1,000 milliliters for every 1 liter, and that leaves us with 0.1 liters, which finally resolves and comes to a solution of 2,500 milligrams per liter. Let's walk through an example how we can use TSS and VSS measurements to measure the performance of the system. In this example, we're going to look at grit removal systems. So first, let's talk about evaluating removal efficiency performance. So the equation at the bottom of the screen kind of walks you through a basic example. Now, we're focusing here on inert suspended solids, which we'll talk about more in detail. But the basic equation for removal efficiency is the initial concentration of something, what's coming in, minus the final, which is what's going out, divided by what was initially coming in, times 100. That gives you percent removal efficiency. So in this example, we're going to be looking at a grit chamber and looking at inert suspended solids removal efficiency across what comes in and comes out of a grit chamber system. Now, most of the times, wastewater treatment plants will just evaluate the system based on looking at how much grit is produced, which is not a bad way to do it. But I would propose that looking at the ISS removal across your grit system is a more direct way to measure the performance of the system. And I'm not saying this is something you want to measure daily. I'm thinking weekly, monthly, every 2 months. Just kind of see how your system's performing. And if you all of a sudden see some change in that performance, maybe it's just something is going on that you're not seeing. You want to take the system down for repair. So we're going to take this equation and apply it to this example here, in which we have a grit chamber in which the influent concentration of TSS and VSS is 300 and 100 milligrams per liter. And the effluent has a TSS and VSS of 250 and 75 milligrams per liter. Now, just a reminder, the total suspended solids, or TSS, is equal to the volatile suspended solids, VSS, plus the inert suspended solids, ISS. So in this example here, as we just walked through it, the initial TSS, or TSSI, that's why we have the I in there, as for initial, is equal to 300, and the VSS initial is 100. The TSS final is 250, and the VSS final is 75. So we're going to take these numbers here and plug into the equation and solve for the removal efficiency for this grit removal system. So in this example, The first thing we need to do is calculate the ISS, both the initial and the final. Once we have that, then we can take those initial and final via ISS and apply it to the removal efficiency equation we had before to solve for a percent removal efficiency. So the ISS initial, what's coming in I, which is coming into the system, is TSSI minus VSSI, which is equal to 300 minus 100, which gives us 200 milligrams per liter. That's our initial ISS. Now our final ISS is equal to TSSF, which is final, minus the VSS final, which is then 250 minus 75, which gives us 175 milligrams per liter of the ISS final. So initial was 200, the final is 175. Now, if we look at the removal efficiency equation, we then put those numbers into the equations we have it there. So we get 200 minus 175. That tells us how much is removed across, divided by what was initially in there, which is the 200 times 100. In this example, we get 12.5% is what our removal efficiency is across the system. And once again, most facilities don't do this, but I think it's not a bad way to track the performance of your grid system, just infrequently, just to see if all of a sudden you see sudden changes, and maybe it gives you a signal that maybe some maintenance is needed. The next parameter we're going to move on to is organics, or organic content. Now, to measure organic content is really difficult because there are numerous different compounds that could be composed of to make organic content, whether that's sugar or pharmaceuticals or some starch or bread. There's a gazillion things that you cannot measure. So the way that we measure this is through a proxy called oxygen demand. And it turns out the oxygen demand is actually a very useful proxy in this situation. Because what the oxygen demand is, it's modeling the effect of depletion of dissolved oxygen that would happen if we discharge this organic material in the river. So what happens is you discharge this organic material in the river, bacteria in the river will then take that organic material, consume it, and as a result of eating that organic material, they will consume oxygen as well. And so that causes a drop in dissolved oxygen in the river, which will harm aquatic life. So by using oxygen demand as our proxy, we number one are able to have a way to measure the organic content, but then also understand its potential impact. And the thing to understand with oxygen demand, and there's two different flavors of oxygen demand that can be experienced. There's aerobic respiration of organic material, which is called carbonaceous oxygen demand. And there's also oxygen demand caused by the process of oxidizing ammonia to nitrate, which is our nitrogenous oxygen demand. We'll be talking more about these in a little bit. So there are many different ways we can measure oxygen demand. There's BOD, CBOD, and COD. BOD, or biochemical oxygen demand, is the oxygen required to remove organic and nitrogen material by decomposition by aerobic bacteria, typically set in a 5-day increment. So in this particular sample, you do and take a sample, you put it into a BOD test, which we'll be talking about a little bit later. You let it sit there for 5 days, and after 5 days, you then measure the amount of oxygen depletion that happens, and that is the way that you measure your biochemical oxygen demand. For carbonaceous biochemical oxygen demand, the test is exactly the same. You take the sample, you put it into a jar, and let it sit for 5 days. But before the test starts, you actually put in an inhibitor that prevents the bacteria that do the nitrogenous oxygen demand, prevents the bacteria that do ammonia oxidation. By doing that, only oxygen that's taken up are those by bacteria that are growing our carbonaceous material. So it's a way that you're able to measure directly the organic content and not the organic content plus the ammonia that's in there as well too. Finally, there's chemical oxygen demand, which is a rapid test, takes hours rather than 5 days as the test may be. And it measures all oxidizable compounds within your sample. While it is an overestimation in terms of the potential impact to what you're maybe if you discharge to a stream, the benefit of this is because you can sample it and get results within a few hours, it's a lot faster. You can respond a little bit quicker. And so sometimes this type of test is used in short term to understand your plant operations and to be able to make adjustments to improve performance before you can get the results from your BOD or CBOD test. So we talked about BOD and COD. Now let's talk about how they interrelate and how they're kind of compare the two. So BOD tests measures soluble organic carbon, is what that measures. Now, if you just do straight up BOD, you can also get some ammonia and nitrite also being captured within that 5 day period. Now, if you do a CBOD test, which inhibits the nitrifying organisms, then it would simply be the soluble organic carbon. But that's kind of how these are related. Now, the COD test measures everything within the BOD test. In addition to that, it measures also iron and manganese and also really complex organic carbon compounds that don't break down within 5 days. So it includes a much broader spectrum of things that can be oxidized. Because of this, for municipal wastewater, COD is typically 2 to 2.2 times BOD concentrations, which you'll typically see within municipal wastewater samples. So, how do you actually measure BOD samples? So, the first thing to know is it's a 5 day digestion. That's why it's called BOD 5. Is it gives it 5 days in which it sits and allows for the organic compounds to be degraded, and then you determine how much oxygen was removed in that period. So that's the first thing that has to be done. Number two, the pH of the sample must be between 6.5 and 7.5, as though the optimal pH needs to be. The sample temperature should be right around 20 degrees Celsius. And another important thing that you need to happen is that um, you must meet what's called the R1D2 rule. So first, I should explain something. So the way the sample is done is you take your sample, you'll dilute it because it's typically much more concentrated. We'll talk about that a little bit. You dilute it in some water. You put it into a bottle, as you see here. Then you'll saturate it with oxygen, and then you'll close it, and you'll allow the bacteria in the sample to degrade over the 5 days. And then after the 5 days, you then measure the dissolved oxygen content after the end of 5 days. And what is required to meet is this R1D2 rule. So, first, with R1, the residual at the end of the test, the residual dissolved oxygen content at the end of the test must be 1 milligram per liter. And the amount of oxygen that was depleted from the beginning to end must be at least 2 milligrams per liter. If you do not meet this rule, then the sample is not valid and you need to redo the sample, is what's required for that. So, that's an important thing to note. Now, in terms of different samples, as I mentioned, you need to dilute it because these are typically highly concentrated samples. And putting it in the bottle, you'll consume all the oxygen. You'll exceed the R1D2 rule. You will not meet that. So typically, you dilute these so that their total concentration is much less than was before. So for inflow wastewater, because BOD can be as low as 40, I've never seen that low, but under rainwater conditions, maybe up to 750 milligrams per liter. So for that, typically you want to dilute it so its final concentration is 1, 2, and 5%. As you go further down in the primary effluent, some of the BODs are removed, and you then go to 2, 5, and 10% dilution. So that the final concentration of the sample is 2 to 5 to 10%. And then finally, for the secondary effluent, typically you're looking between 10, 20, and 50% final concentration of your sample because of the fact that the BOD concentrations are now between 4 to 75 milligrams per liter. So now we're going to walk through how you're able to do a dilution calculation to be able to meet those dilution concentration requirements for a valid BOD analysis. So the way I like to do this is using dilution formula, which also we call the C1V1 C2V2 equation as well too. So in this situation, typically what you're trying to do is you're trying to solve for one of these. And in the situation in which you're looking to do dilution, you're typically trying to figure out what your initial volume of sample you need to add to the final bottle to be able to determine to meet the dilution that you need to meet. So the way the equation works from a simple mathematics perspective is the concentration initially times the volume initially is equal to the concentration at the end times the volume at the end. And so we'll walk through exactly how you can use this and how this equation can be used to determine the amount of sample you need to add to meet a certain dilution requirement. Now let's walk through an example of how we can use C1, V1, C2, V2. In this example, we're going to solve for C1. So how do we do that? How do we solve for C1 using this equation? Well, one way we can do this is by dividing both sides of the equation by V1. So we divide left side by V1, the right side by V1. Because the left side has V1 on the top, It's just like dividing 2 divided by 2. That is equal to 1. So effectively, that goes away and that is gone at this point. On the opposite side now, though, we moved V1 to the other side. So in this situation, C1 is equal to C2 times V2 divided by V1. So if we want to solve for the initial concentration situation, in which we know the final concentration, final volume, and the initial volume, we can then use this equation to do that. So let's walk through an actual example for BOD dilutions in which we are going to solve for how much sample we need to add so that we meet the dilution amount of 10%, 20%, and 50%. So in this example, the final bottle that we want to fill up, the BOD bottle, is a 300 milliliter bottle. So in this situation, we're solving for V1. We know what the concentration is initially. In this case, we're going to assume the concentration is 100%. We know the final volume, so we want to just solve for V1 in this case. So using the exact same equation we just used in the previous slide, we're going to solve for V1. As you can see, the C1s cancel out. And so now we're left with V1 is equal to C2 times V2 divided by C1. So going through the equation, let's list our knowns. C1, as I mentioned earlier, is 100%. That's our undiluted sample. It is not diluted, so it's 100%. C2 is going to be 10, 20, or 50%, depending upon the 3 different bottles we have. And the V2, the actual BOD bottle sample volume, is 300 mLs. So now we can take this equation, the V1 is equal to C2, V2 divided by C1, to solve for how much volume we need to add of our sample to meet these 3 different concentration or percentages. So in the case of the first bottle, our C2 is 10%, our volume is 300 mLs, and our initial concentration is 100%. So it's 10 times 300 divided by 100 gives us 30 mLs. Because the percentages are in the top and the bottom, those both go away. And we're left with 300 mLs as our unit. So we're left with 30 mLs as our undiluted sample we need to add to a 300 ml bottle to be able to make that a 10% dilution. For 20%, we do the exact same thing. We substitute the 10% for 20%. Now the math works out to be 60 mLs of undiluted sample. Notice 60 is double of 30, and 10 is double of 20. So the math works out and you feel comfortable with that in terms of the analysis. And now for the 50% dilution factor, now we just change out 50% for 20%. So 50% times 300 divided by 100%, that gives us 150 mLs, in which half of 300 mLs is 150. So the math, once again, adds up. There are many different ways that you can do BOD testing. There's seeded and unseeded. Unseeded is when you just take your sample, add it to the bottle, there's natural bacteria in your sample, and it performs the analysis. There are some times, though, in which a seed, additional bacteria, needed to help drive the reaction. And so the seed can be a couple different sources. You can find a natural source. Say if you happen to be doing BOD tests on your final effluent after it's been disinfected, you can grab some primary effluent, just a tiny bit, add it into there, and then that provides you your natural seed. Or there are certain commercial vendors that will sell a seed that you can buy as well. Now, when do you need to use the seed? There's several different reasons why you need to add a seed. Number one, if the sample had to be neutralized, if the sample originally was greater than 8 or less than 6, that could definitely make the environment less hospitable for bacteria. And so by bringing the pH back 7, you may not have bacteria present in that sample to where they at least be effective enough to consume the oxygen. So you may need to see that situation. Also, the sample has been dechlorinated. That process can also kill the bacteria. So you may need to add a seed that situation. Also, there's just some times where, for whatever reason, there's just not enough bacteria in your sample. So you do not meet the R1D2 rule. And the result of that, maybe a seed is needed then as well. Let's walk through how you calculate BOD when you run a BOD sample. So the basic equation for BOD is the dissolved oxygen initially minus the dissolved oxygen at the end of the 5 days times the sample bottle size, that the final bottle that you used, divided by how much of your sample you put into that bottle. Remember, we have to dilute this, so you don't always put the entire sample bottle volume of your sample in there. In some cases, you're only adding 1% or 5% or 50% of the total bottle volume is your sample there. So it's something to think about. So it's DO initially minus DO final times the BOD bottle volume divided by the sample volume that you put into that bottle. So that's how you calculate. So in our example here, we've got a 24-hour composite sample in which you took 30 mLs of a concentrate sample, put into a 300 ml BOD bottle, and then you put it into the test. And the initial DO reading was 8.5 milligrams per liter, and the final DO reading was 6.0 milligrams per liter. The question is, what is the BOD of this sample? What is the final BOD concentration based upon this analysis here? Let's define our knowns. The DO initial is 8 milligrams per liter. The DO final is 6.5 milligrams per liter. The sample volume we added to the BOD bottle was 30 mLs, and the bottle itself is 300 mLs. We take the equation we have here that we just mentioned before. We then plug in our knowns. We get an answer of 15 milligrams per liter. Now, that was an example of the equation if you had an unseeded BOD sample. If you need to add a seed, you have to go through the process of doing a seed correction factor, which effectively accounts for the amount of BOD you may be adding, since the seed itself would likely have its own BOD concentration, BOD effect. And so you take the difference between the DO initial minus DO final and subtract from that what we call the seed correction factor. And without going too detailed into this, you can look at the equation below. It effectively accounts for how much BOD the seed has, and it accounts for the fact that it's been diluted a couple of times. And that's what your seed correction factor is. It just removes the DO that would have been present caused by the seed being added. So this graph kind of provides a rough representation of the BOD present in a seeded BOD sample analysis. A good portion of it is the BOD example exerted by your sample, but there is a portion of it that is taken up because you added the seed into it, which it has its own BOD impact. And so you need to correct for that. So I want to slightly change the subjects, but it's an important laboratory analysis principle that I do want to cover, is how you can also use the C1V1, C2, V2, other than things like BOD dilution, where we were dealing with percentages. In this example, we're dealing with concentration we're dealing with. So in this example, we have a 50 ml stock solution of ferric chloride at 100 milligrams per liter. And we want to dilute this so that we get the concentration of ferric chloride down to 20 milligrams per liter. The question is, how much, how would we make that solution? How do we do that? And so in this example, we can use the C1V1, C2V2 equation to solve for this. Now, if we want to solve, in this example, we're going to solve for V2, which is what our final concentration would need to be. So we'll just rearrange the equation. So now V2 is equal to C1 times V1 divided by C2. We get that by dividing both sides of the equation by C2. On the right side of the equation, the C2 goes away, and we're left V2 by itself, and we're left with C1 times V1 divided by C2 is equal to V2. And so that's how we solve for that equation. So our initial V1, our volume of our sample, is 50 mLs. And our concentration, or C1, is 100 milligrams per liter. What we're looking for our C2 is a concentration of 20 milligrams per liter. So now we need to know what the final volume needs to be able to be 20 milligrams per liter. So what was that final, what do we need to dilute the sample with? So in this equation here, we take C1 times V1. So that is C1, 100 times 50, which is the 50 mLs. Divide that by C2, which is our 20 milligrams per liter, and that gives us a V2 of 250 mLs. So what this is telling us is our final volume needs to be 250 mLs. Because our initial volume sample is 50 mLs, that means we need to add 200 mLs of water to that sample, that V1 sample, add 200 mLs of water to get the final volume of 250. And at that point, then we'll have a concentration of a ferrochloride being 20 milligrams per liter. As I said, this equation C1V1, C2V2 can be used in multiple instances, whether it's percentages, percent dilution, like we're talking about with BOD bottles, or concentrations, such as this, or even determining how much you need to feed of a particular solution to meet a concentration within a pipe if you're doing like a feed pump type situation. So it is a very useful tool to be able to do this. So we talked about organics. Now we're going to move on to the next parameter, which is inorganics. So there's multiple inorganic compounds that you may want to measure for your wastewater treatment plant. There's nitrogen compounds, including ammonia, nitrite, and nitrate. These are typically or sometimes included in your discharge permit in terms of limiting how much of each one of these you can discharge. There's phosphorus, which is less frequently, but can be in a discharge permit, where you're looking at either total phosphorus or orthophosphate, what's required to measure your discharge permit to make sure you don't exceed the discharge, once again, less frequently. Um, while not necessarily within your permit, but measuring sulfate and hydrogen sulfide is important because sulfate can be reduced under anaerobic conditions to hydrogen sulfide. And hydrogen sulfide is corrosive. Number one, it's typically why your head works would be a little bit more corroded because hydrogen sulfide is present there. Number two, high concentration of hydrogen sulfide also is not healthy for humans. Other organic compounds you typically measure is your chlorine, talking about your chlorine residuals, and we'll talk about that in later modules. And also other important inorganic compounds include alkalinity, which we're going to talk about more specifically with the nitrification in later modules. And then also pH, which is a measure of how acidic or basic your samples are. Now, for the next sections, we're going to be focusing on nitrogen and pH. As I said later on, we'll be talking a little bit more about alkalinity and chloride residuals. First parameter we're going to talk about is pH. pH is a measurement of the amount of hydrogen ions are in your water. So your water typically is a balance between hydrogen ions and hydroxyl groups. And when you have more hydrogen ions, you have less hydroxyl, and vice versa. When you have more hydroxyl ions, you have less hydrogen ions, typically the way it works. And so at a neutral pH, a pH of 7, you have an equal balance between hydrogen ions and hydroxyl ions. As you go acidic, though, you have more hydrogen ions, and your pH will drop less than 7. That's what we call acidic, as I mentioned before. And as you have less hydrogen ions and more hydroxyl ions, that is more of a basic condition, which means a pH of a level higher than 7, up to 14. And that is your basic range we're talking about there. So looking at the range of pHs to provide some examples, so you have a kind of a understanding in terms of what's more acidic and what's more basic. Let's first start with what's neutral. So water is typically pure water that's pH of 7, that's neutrally balanced. That is pH of 7. That's a balance between hydroxyl ions and hydrogen ions. Now, as you go a little bit more acidic, we're talking about things like coffee, Coke and Pepsi, lemon juice. All those go a little bit more acidic, and the more on the acidic side, the little bit more dangerous and corrosive they are, the more potential injuries they can have. So something that's got pH, on the lower end can potentially cause damage to human health and cause irritation and maybe burning of your skin kind of thing. So be mindful of that. Now, on the flip side, things that are more alkaline or basic include baking soda, hand soap, bleach, caustic soda. These also, as you go higher, can also cause similar issues. So just this scale kind of provides you a rough range of understanding about the different pH ranges that we were concerning. Now, pH, as I mentioned before, is frequently a discharge limit for your wastewater treatment plant. And each plant is different, but typically a range between 6 to 9 is a typical discharge range. Once again, every facility is different, and your pH discharge for your wastewater treatment plant may be different than that. But that kind of is a standard range. We're trying to keep near neutral and not going too alkaline or too acidic. Let's move on to nitrogen. Nitrogen can be measured in different compounds in wastewater. Typically, we'll think about total nitrogen as all the nitrogen that's in the wastewater, but it can be divided into two main branches. One is total inorganic nitrogen, which is made up of 3 species: nitrite, nitrate, and total ammonia nitrogen, which can be present as ammonium or ammonia gas. Besides inorganic nitrogen, Organic nitrogen is also present as organic nitrogen, which is nitrogen bound up in organic compounds like protein, urea, nucleic acids. When we think about which ones are important for wastewater treatment, typically we'll think about ammonia and what the ammonia is coming to wastewater treatment plant. But depending upon if that happens to be part of your discharge limit. But you also do want to think about organic nitrogen because in the wastewater treatment plant, organic nitrogen can be converted to ammonia. And so the ammonia that you measure plus the inorganic nitrogen that can be converted to ammonia represents kind of like the total potential ammonia load to wastewater treatment plant. And interestingly, that total of total ammonium plus organic nitrogen is measured through this test called the total Kjeldahl nitrogen test, which measures both of those combined. So if you're looking to understand your wastewater treatment plant in terms of the total potential ammonia load to your treatment plant that you need to treat, measuring the total Kjeldahl nitrogen to your plant is important. Now, also just measuring, once again, each of these three different inorganic species is important because those are potentially your discharge limits you have for a treatment plant. And then sometimes, in some locations, you may have a total inorganic nitrogen limit, which limits the amount of total inorganic nitrogen discharge because that can potentially lead to eutrophication of receiving water bodies. So let's talk a little bit more about nitrogen as well as how pH can impact nitrogen. Specifically, we're talking about ammonia and how ammonia in its different forms changes. As we talked about before, total ammonia nitrogen includes both ammonium, which is the NH4 plus, and ammonia gas, which is NH3. Now, this graph here shows how pH, as the pH goes from 5 to 13, how the species of ammonia changes from ammonium at less than 9, it's more ammonium. And as you get closer to 9 and go past that, it becomes more ammonia gas. And why that's important is that most wastewater treatment plants are operating right around 7 to 8 pH, which means then that for the most part, all of your ammonia is present as ammonium, which is the positively charged form, and that form likes to stay dissolved in water because it's positively charged. So, in your aeration basins, your ammonia wants to stay in the water because it's positively charged. It is not in the form of ammonia gas, in which it would then bubble off if it was happened to be the case, but it's not. And so, the only way to really remove ammonia from your wastewater, if you need to do it, is a biological process under standard wastewater conditions in which the pH is right around 7 to 8. We'll be talking about that next. So, as I just mentioned, there is a biological process that can actually remove ammonia from and nitrogen from wastewater. First is the process called nitrification, which uses a bacteria called nitrifiers, which convert ammonium to nitrate. Now, once again, that's the process called nitrification. And then if your system is actually set up for this, you can, if you have a denitrification zone, there are a set of bacteria called denitrifiers that will take that nitrate and convert it to nitrogen gas. And at that point, the nitrogen gas will be removed by volatilization. But each of these are different bacteria. They require very different environments, which will be discussed in the secondary treatment process portion of this presentation. The next water quality parameter we're going to talk about is pathogens. So, pathogens are obviously specific bacteria that can cause harm to human health. And so that can include bacteria, viruses, protozoa. There's many, many different things. But for measuring it, we typically use what we call fecal indicators. These are organisms that are indicator organisms that are determined to be good proxies for other pathogens. So you know if you remove these fecal indicators, you will also remove these other pathogens. So ultimately, for your wastewater treatment plant, you need to evaluate what your wastewater treatment plant is permitted for in terms of what pathogen that needs to be removed, and make sure that you do remove those pathogens to meet the discharge permanent limit. Now, think about pathogens and what is tested. There are typically, for wastewater treatment plants, three different parameters that are used as pathogen indicators. Very common one that's used in Arizona is E. coli. E. coli is one species, although there's many different strains, but we won't worry about that. But this typically is present in animal and human waste. And so it's a very good specific measurement of how you've killed this specific organism in your wastewater treatment plant. So once again, several facilities has this as their permit limit for what they need to meet. Now, there's another indicator called fecal coliform, which includes E. coli plus six other species that are also in animal and human waste. So it's a little bit bigger of a picture in terms of organisms. And so some wastewater treatment plants will have that as their wastewater treatment plant discharge limit for ensuring that they remove pathogens. Now, there's also another group that's larger called total coliform, which includes 16 species, which are also those found in soil and vegetation. Once again, just a different indicator, but ultimately looking to identify that to remove pathogens. Another test that is done usually annually for wastewater treatment plants is called the WET test or whole effluent toxicity test. This typically is an annual test that will take your wastewater and dilute it and will then expose certain key indicator organisms like fathead minnows or common water flea, expose them to that and determine if they die. And the main reason why this test is performed is to identify if there's any toxic compounds in your wastewater that is not captured by the traditional tests. Unfortunately, we cannot test for everything. So this is a rough way that is used to understand if there's something else going on at your treatment plant that is just unknown because maybe you have an industrial discharger that's discharging to your treatment plant that is causing some potential harm in the environment. This is a way to be able to measure it. So just an important test to think about. And most of the time, these tests are performed at third-party labs because the amount of testing and credentials needed for this are pretty extensive. Now we're going to talk about laboratory analysis, specifically why you want to do laboratory analysis, proper record keeping associated with it, how you collect the samples, and different instruments you can use as part of the laboratory analysis that you'll need for your wastewater treatment plant. To start off, I would definitely support all facilities to log their operational data into some Excel spreadsheet where they can track and graph the performance of their wastewater treatment plant. The key reason why is number one, it just provides a nice graphical representation of regulatory compliance. It is good record keeping and also allows you to understand seasonal variation in your treatment plant, or maybe be able to identify situations in which your treatment plant starts performance starts hurting that maybe you miss if you don't look at the trends. So all those reasons why is one of the reasons why I definitely support doing some type of operational data tracking for your facility. Now, ultimately, collecting the sample, there's a couple different methods that are done for collecting sample. There's manual sample collection or grab samples and automated sampling, which we'll talk about next. So grab samples or catch samples are typically collected from one location. The duration is less than 15 minutes. You just collect a quick sample. Sometimes these are used for parameters that have short hold times, like pH, temperature, or bacteria, in which you just need to grab a quick sample. So through the sample, through the wastewater, you just grab a quick sample, and now you do the analysis. Once again, some tests it's appropriate, other tests, and mostly for compliance purposes, you need to do what's called composite samples, which are samples that are collected over a 24-hour time period. What this does is this can be done by either collecting discrete samples yourself or through automated ways of collecting samples, either through doing a time weighted sample where you sample every 15 minutes, or flow weighted, which you collect more samples during heavier flow periods and less samples during lower flow periods. That type of sampling, the flow weighted sample, is considered the more accurate because it collects a complete average of the total volume of wastewater treatment plant collected over your sample, rather than doing a time weighted or a manual discrete sampling mixing that could happen as well. Now, there are many different laboratory analysis equipment that can be used. There is the ISCO composite sampler, which is that type of sampler that can be employed on the field for doing flow or time weighted composite sampling. As an example of a BOD measurement test, we got a laboratory scale, which can be used as part of many testing, including TSS sampling along with laboratory oven, and then also a spectrophotometer that can be used for lab tests on ammonia, phosphorus, and COD. For any laboratory analysis, proper QA/QC principles are important. First, make sure your samples are representative of what you're collecting. Make sure they're well mixed, they're timely, and appropriately, and they're sampled at the right location. You want to make sure that the samples make sense. Also, you want to make sure they're reproducible. So by doing duplicates and following standard operating procedures are very important. Also, make sure that you label your samples clearly. The labels include the sample name, the date, the name of the person collecting it. Everything is extremely legible. Otherwise, there could be confusion at the laboratory. The important thing is to make sure that this is defensible data and also very useful data. In the next few slides, we're going to cover conservation of mass. While it's not covered in huge amounts of detail during this module, it's an important principle to understand as you move forward throughout your career. One important principle to discuss is conservation of mass. What this means is that all mass is conserved, so it can change state or can change chemical composition, but it never disappears. This same principle applies to wastewater treatment processes, no matter what process it is, whether chemical, biological, or physical, mass exists. It just changes forms, sometimes for what we want, sometimes for not what we want. So as an example of conservation of mass, let's walk through a simple acid-base reaction. In this particular reaction, we have hydrochloric acid, which is a strong acid, reacting with sodium hydroxide, which is a strong base, to form water and table salt, the sodium chloride. So if we look at each of the individual molecules that are part of this, hydrochloric acid is made up of a hydrogen proton and a chloride ion. Sodium hydroxide is made up of sodium ion and hydroxyl ion. Under these conditions, when you combine these two together, the hydrogen ion and the hydroxyl ion will react, combine, and form water. The sodium and the chloride, because they're within water, will stay dissolved. If there is enough sodium and chloride present, it could potentially precipitate out, but because the water is a nice solute in which the sodium and chloride can stay soluble in, it will just stay dissolved there in the current state. Now, as you can see, none of the atoms disappear. They all just change state. And that's one of the important principles as part of this, is that ultimately we just had this basic reaction that transformed the different atoms into new products as part of this. So now we're going to talk about some fundamentals of how you can apply analysis to wastewater treatment plant performance. So you've measured all these different parameters. One important thing to evaluate is a plant capacity evaluation of your treatment plant. When I think about plant capacity, I think about two main parameters. So number one, the loading rate to your facility, how much BOD, TSS, nitrogen, phosphorus, whatever it may be, that is loading in like pounds per day to your facility. And number two, of course, is the hydraulic load rate. We're talking about this basically the volume of water that the system can be treated as well too. The reason why this is important, number one, the hydraulic loading rate, I think, is pretty apparent. You push too much water through your system, you can cause all sorts of issues in terms of, much shorter reaction time in your systems. You can wash out areas. You can also overflow weirs or even overflow structures. And that is clearly not something that is ideal. But in terms of the loading rate, that is ultimately determining what the capacity of your plant is to be able to treat a certain pound of material. And so if you exceed that amount of loading, then your clarifiers, your aeration bases may be overloaded with the amount of stuff it's designed to handle and will not perform as needed in the case. And one of the primary examples I like to think about it as is if you get too much BOD loading to your facility, that can overload your aeration basins and your blowers cannot keep up with the amount of oxygen that is needed to be consumed as part of that. And so as a result, the DO and your aeration basins will drop and you may get incomplete treatment as a result of that. So as a result, your wastewater treatment plant and all unit processes have a max design loading rate that you need to understand and then calculate what's actually being delivered to those to make sure that your facility is able to keep up, to make sure that it is able to meet the performance requirements it's designed to make. And if it is overloaded, then maybe you need to look at either number one, expanding your facility, or number two, looking at the loadings to your treatment plant to maybe evaluate if certain users are overloading your system potentially. This is an example of a treatment plant in which we were tracking the wastewater treatment plant loading to the facility. The client was concerned that some discharges were causing the plant to exceed its rated limit. In this situation, the rated limit for the plant was right around 5,800 pounds per day of BOD. We actually looked at the inflow data to come to the treatment plant. Well, that tells a very different story where even under the high flow days, high loading days, we are well below the actual maximum loaded rated capacity of the plant. So that's why it's important to track your data and to be able to understand the loading to your plant compared to how it's rated. So to give an example of how to calculate the loading rate, it's a pretty simple equation that I use very frequently. The loading rate in pounds per day is equal to the flow in million gallons per day times the concentration in milligrams per liter times 8.34, which is our conversion factor. So in this example, say we have a wastewater treatment plant that receives 15 million gallons per day of flow and the BOD concentration of 300 milligrams per liter. What is the loading rate in pounds per day of BOD in this example here? Well, here's a very long, drawn out kind of working through the math of all the unit conversions that will get you to this solution, in which the solution is 37,530 pounds per day. But if you just simply take the 15 MGD or 15 times 300 times 8.34, that'll give you the same answer. So it's important to know how this equation is derived, but for a shortcut, if you want to know the pounds per day loading, it's just the flow times MGD, the concentration in milligrams per liter times 8.34 will give you your answer. And that concludes our introduction to wastewater treatment, water quality, and laboratory analysis. Thank you for listening to this module. We hope you join us for the next module, which will be covering preliminary treatment.